So my perspective is from the other end of the scale, basically. Instead of looking at stuff that is the size of an ocean, I look at something that is the size of, a bathtub, basically. And so I'm basically going to talk about bed load transport of mud in forms of aggregates of various type. And so we got just go to the next slide here. And okay, how do I transport my slides? Okay, here we go. All right, it's a bit slow. So basically, for longest time, there has been a body of literature where people have told you what shales and mudstones are and how they should behave. The only problem when I got started on working on these things, it was already clear from my first studies that it probably isn't that way. And so my field studies basically suggested, that was 40 years ago or more, 50 years ago, that mudstones are much more interesting and dynamic in terms of depositional scenario than what's in the literature. And then later on, I got into flume studies and showed actually the underlying processes that form these the observed sedimentary features in mudstones and how mudstone beds accumulate. And so we basically took care of decades of learned opinions and put them out of their misery by doing a few good experiments. So at the beginning, of course, when I started, this was in the 80s. We looked at mudstones were not very popular really, so I didn't have a lot of turquoise to work with, and so we did a lot of outcrop studies and took very large samples and did detailed studies on those, and then we realized that instead of relatively featureless and homogeneous, we had multiple flavors of mudstones in there. They were very heterogeneous, and they obviously accumulated discontinuously, a lot of interruptions in the record. And the sedimentary structures that were preserved hinted at processes that were thought to be unapplicable to mudstone deposition. And so that basically, but on the other hand, doing detailed facies studies is something that was very doable back then, and it's very doable today. You do it right, you can get lots of insights about processes that deposited your mudstone, and the only thing you have to do is don't be afraid of what other people think. Just let the rocks talk, basically. And so this is basically one of the early studies that we did in the Catskill Delta, and that's the Sonia group. We were able to learn a lot from those mudstones simply by looking at outcrops and head specimens and thin sections. But I also learned in those early studies is that, in the early 80s, sequence stratigraphy just came on the scene, and it was usually something that you did with sandstones, not with mudstones. But looking at these mudstones that I worked on back then, you could see already that there is, this is all mudstone, bottom to top. Okay, there's not a single sand grain in here, but you can see that there's non-parallel bedding. There's packages that have different orientations. You see truncation surfaces going through, and you see that there's straddle down lap. Layers literally end at the bottom of that truncation surface. And so in sequence stratigraphy speak, of course, that would mean sea level fluctuations and lateral transport of mud. And that was sort of like, that was not in the textbooks. It was not allowed at all at that time. And so it was a bit of an upriver swim, to say the least, to get this kind of conceptual change accepted. The experimental starting point when we started experimenting with this was, let's try to understand lamination, because lamination is ubiquitous in shales. And there's this picture, is a typical laminated shales, and thin sections like this are all over the literature in the early days, and usually interpret that, okay, sediment was slowly settling down from above, and you have multiple settling events stacked on top of each other, and that was it, end of story. But the problem is, when you start looking at these sediments, you notice that there's two kinds of lamina. There's lamina where you have, I mean, look at this thing. It's not even a millimeter thick, this lamina, and it has load structures in it, flame structures and so forth. And you see here the modern one, same thing. You have lamina that have lots of load structures in it. So that's one type of lamina. The previous one we saw was very nice flat lamina. And then you have here the lamina with irregular bottoms, and obviously stuff was settling from the top. I have no problem with that. And load structures form. So why are the load structures visible in some places and not visible in others? If this also should be physical settling, why shouldn't it look like this? So we have basically to think about what this all means. And so we have here basically, when we sort of have a scenario where physical settling is the main process, and we've replicated things like this in laboratory, in tank experiments. We saw the exact same thing happening. And then how does that contrast with these flat lamina? And that is basically sort of a very fundamental divide here. Here is, on one hand, on the left side, you have gravity bringing things down to the bottom. And on the other hand, what happens here? That's the question. And the thing was that there were little hints in these laminated deposits, like little lenses of sand here, and maybe sometimes some very low angle dips of the lamina and stuff like this. So there's some slight non-parallelity of lamina, and if you have a good day, you can say, yeah, maybe it was not settling, maybe it was currents. What else do we have available to do this? And so that sort of was a mental starting point for saying, okay, let's simply have a flume where we can push muddy suspensions through and see what happens. And that's basically this one here. So we had basically modern and ancient mudstones that contain a lot of sedimentary features. If you look at them, thin sections, polished slabs, and so forth, there's you see a lot. And so you see these sedimentary features, you can make deductions about depositional parameters, but you are so far out at one side of the scale spectrum that your deductions are qualitative at best. There's no experimental work to back up anything that you're seeing out there. And so it was basically obvious that we need to do experimental studies in order to get the wherewithal to make accurate interpretations of the rock record with respect to flow velocity, bed shear, and things like this. And so objectives were basically to look at mud and mud deposition under energetic conditions and see what was depositional and erosional parameters, the thresholds, the rates, and then one important thing was fluctuation. That is sort of the key of it all. And what kind of bed forms and deposition of fabrics do we get? And for this kind of stuff, flume studies are perfect because we can control the parameters like sediment concentration, salinity, flow velocity, and shear stress. And then we do get beds of mud, we get bed forms and deposition of fabrics that we can make visible by taking that flume deposit and turning it into a rock and thin sectioning and all that kind of stuff. It's a little tedious, but it's doable, and we have done it. The one thing about flume experiments with muddy suspension is, however, that the waters are murky. You basically don't see anything. It's not like a sand flume experiment where you see beautiful ripples moving along. initially, when you do this with mud, you see nothing. You just see a brown soup, and that's it. And so we had to do a little bit, how should I say, we had to be creative to start to see. But what we found when we did those flume experiments, where we moved mud around in circles basically, and that if you have a muddy suspension, and when you having the proper flow velocities, then mud flocculates and forms bedload floccules, and those floccules can form ripples, and then those ripples can accrete to form mudstone beds. And the flow velocities for that are comparable to what you need for bedload transport of sand grains. Okay, so you could run this experiment with sand grains, and it would make ripples and form beds. You can make this experiment with mud, you get ripples, you get beds. Just one of them with much more water. And so when it compacts, of course, you barely see it. This is basically what you see initially. You see this is an example of a large Balkan ripple basically moving across a flume bottom. And this is just one of them, but you could look to the left, to the left and right. You see multiple of migrating through there. If I increase the rate of deposition, I get, instead of getting Balkans, I get more or less sort of wavy linear ripples basically, pretty much to what the previous speaker showed in her pictures. And it's about the same scale. So we have here mud ripples that incidentally are a similar scale of sand ripples that if you had the sand. And so when I see those deep sea pictures, I'm surely tempted to ask one question. So what is the grain size of the sediment? What is it? Is it mud or is it actual sand? Because looking at the geometry and the morphology of these things, you can't really tell the difference. Anyway, so once those experiments had successfully shown that we can transport mud in bed load in the form of floccules and build up beds and so forth, and we have been able to show that this is reflected directly in the rock record, there's no question about it. We ran experiments on various other aspects of this whole story, about 20 years now. And we're trying to arrive at a physical foundation to understand mud transport and deposition. We have come some distance, but it's a lot of work because we're the only lab that is doing it actually. But we're operating from a 4-dimensional experimental matrix where we're looking at velocity, sediment concentration, salinity, and then also already mineralogy and particle type. And then we are working on the role of organic matter, which has just been published a few days ago. And then but another thing that we probably have to engage in the future is to look at sediment mixtures. How does this stuff behave? You have different kinds of clay or certain silt and clay ratios and sand involved and so forth. For example, I mean, I already said sand and mud floccules move under similar flow velocities, and we can actually have experiments where we have mud plus mineral sand grains, I mean quartz grains, and we run them at flow velocities that are above the threshold of motion for both. What we get interbedded, interlaminated sand and mud that was both deposited by the same current at the same time. Okay, and we still learn new things with each new experiment. I mean, we're having 2 flumes running with experiments right now, and we constantly run into surprises. But the surprises are not of the type that they would change the paradigm, quite the opposite, but they're telling us new aspects of the larger system, basically. So we're on a good way, but it would be nice if some other labs would jump up to the rise to the occasion, let's put it this way. It's a lot of work to be done. But anyway, we have by now proven investigative techniques of how to study muddy systems. And this is, for example, an example how we do this. We run them through experiments where we start at full suspension and then we sort of slowly step it down. And at some point, I mean, these kind of curves like this from on the part A of the diagram, that's simply sediment loss in the flume and corners and nooks and crannies and so forth. That's inevitable. You can't build a flume that has no blind spots, basically. Or if you can, it's going to be bloody expensive. But at some point, you come to a hydraulic condition where the mud really comes out, forms bedroot floccules, and then the decline curves get much steeper. And this happens around here. And then you go even further, and it becomes more dramatic. The other thing that you notice that salinity, you have here fresh waters, 2%, 3.5%, is not really the deciding factor of how this happens. Okay. Basically, no matter which salinity you use, once you reach a critical velocity, stuff comes out. And which is sort of, and we also played with a range of sediment concentrations. And basically, sediment concentration that you can imagine in nature to happen in tidal channels or in river channels and so forth would perfectly behave themselves like this. So the important thing is mud gets deposited because of the floccule formation at much higher velocities than the literature gives it credit for usually. And so then, you can see that here's just the flow velocities, and you see that for this particular case, at about 25 centimeters, it gets coarser no matter what you do. This is sort of a sharp dividing line here. And you can do floccule counting and show it graphically as size plots, so that the floccules get larger as bed shear drops, become more stable. And the critical velocity is indifferent to a wide range of salinities and suspended sediment concentrations, but is still dependent on minerals, okay? Different minerals have different thresholds, basically. So we have results that pretty much have stood the test of time. And for mud, basically, arriving at the bottom by gravity settling is the easy part. They all do that, no matter where you are. Gravity is your friend. But the fact of the matter is also that at most ocean basins, the water is not stagnant. It moves. Currents are common, and currents can and will move mud. Anything that arrives at the top of a bottom current will get mixed in with it and then move along with it, and it will flocculate and it will make little ripples. So these bottom currents are strong enough to move mud in suspension. For sure, and when flow velocity falls below the critical velocity of sedimentation or the shear stresses associated with that, you get sand-sized floccules that move in bed load, they form ripples and build up muddy strata. And the cool thing about it is that this is basically water depth independent, okay? And the things that we show in most of our experiments as sort of centimeter scale ripples, maybe spaced 10, 15 centimeters apart or something like this. And those are basically the workhorses of transport, of mud transport, when there's currents with suspended material moving on. They always will make these ripples, but then the ripples can become part of larger bed forms. You get mega ripples. We have fossil examples of that. And I would venture that even larger muddy bed forms in the deep sea are basically built ultimately by these centimeter scale ripples that migrate up one side and then deposit the sediment on the other. As I said already, these processes are largely insensitive to sediment concentration and salinity and reflect mostly mineral properties, and they're also prone to biological modification. In our experiments, when the experiment runs too long, even if we start with a clean flume and mineral dust and stuff like this, after some time, there's biofilms forming, and they change the behavior of things immeasurably within a week or something like this. And so out in the open ocean and so forth, where there's no shortage of organic matter, the pure mineral behavior that we are trying to capture in flumes is modified by biological processes, but it's all good because it usually tends to increase or raise the thresholds for the critical velocity and stuff like this. So actually, it makes the mud deposit easier up to a point. Everything is like that. So everything fluctuates once it's small enough. And we can do experiments like this with quartz sand. We will fluctuate when it's fine enough. And mudstones can be composed of floccules. Wait a moment, sorry. We can have, so we have floccules is one way mud aggregates. Then we also have, if there's a muddy substrate, it can be ripped up by currents, and little bits and pieces of that millimeter size will be transported. They're slightly denser than floccules, but not much. They behave pretty much the same. And then we also have mudstone lithix, or in most mudstones, a combination thereof. And so deciding which one you are looking at, what type of mud aggregate, you have to use high-end petrography, but it's technically a simple matter. Your understanding starts at the petrographic level when you understand what kind of aggregates you used to have when this stuff was deposited. And the process that I described, the aggregation into floccules and transport of bedload mud and stuff like this, works in a roadside ditch just as well as in deep sea, and it's easy to watch. Ultimately, whatever you do with the mud, the final current wins. This is just an example of, this is a roadside ditch after a bit of a rain. And so you can see the muddy suspension moving through here. You can see here small bed forms forming into channel here. Okay, this stuff is very watery. It's 80% plus water, basically. It's liquid, more or less. You try to touch it. And here this forms nice ripples. Okay, rippled stuff, bang. And it's all mud. Okay, and this is basically a roadside ditch, and I don't imagine that the rules change, but just because you have a kilometer of water on top of it. So a lot of this, the deep sea drifts, contourites, when they're quite muddy, which sort of some of them are, it's probably this is a process that I just described that actually allows the mud to move and to get deposited in nicely layered deposits. And just to show you what the mud aggregates look like, here this would be the floccules that we produce, for example, in flumes, and which also have been observed in natural deposits, in natural settings. Then we have, for example, fecal pellets is another category of mud aggregates, and they travel together, they form sand-sized particles, and they're fine-grained, and they get compacted and flattened over time. This one is lots of coccoliths, basically. And then you have here, this is a more generic ancient deposit, lots of different kinds of muddy, flattened aggregates in there. These are probably wrap-ups from the massive substrate somewhere else. And then finally, you have mudstone lithix like this one here, which are also part of many mudstones, because just because mud weathers on outcrop doesn't mean it completely breaks down. Oftentimes, a certain part of the outcrop travels as sand-sized and silt-sized fragments of that mudstone instead of as individual mineral grains that you see here. And the consequences of this is, of course, this here, for example, I got this sample from the Adriatic, and I was told it's a mudstone, a mud. Sorry, there was lots of water in it. This is a mud that I was sent, 200 microns here. But when you prepare it properly so that you can see the individual particles, and it's not easy. I mean, this is 80% water when it was collected, okay? So, but we have our ways to do this, and you can see there's definitely not mud particles, mud-sized particles, and see here that actually you have rounded, fragments here that are basically the mudstones that came out of a river not too far away. Mudstone, the river basically spit out suspended material, but it also spits out a whole bunch of fragmented, transported mudstone lithix, basically. And so you take one of the Schlumberger tools to tell you what kind of rock you have when you drill it. That it would, of course, return this as a mudstone, but hydraulically, you're looking at a sandstone. And so that will tend to throw you off quite a bit if you don't look at the rock itself. So you have to trust your eyes, because that's where the insight really starts. This is just to give you an idea. This is in the flume experiment, and you can see that we have a clay bed that has markers in it, and we have a slight clinoforms forming, basically. And then you see when you break these layers apart, you see ribbon furrow structure in it, and you know that every one of these layers has been accreted and deposited by migrating ripples, and not by stuff falling out of the water column. And you find these same textures in the rock record. It's just to give you an idea of how this works. We have an experiment here that ran for about a week, or actually several weeks, but this is the first week of it. And we simply film from this transmitted light how the ripples are moving by. And every time a ripple moves by, it leaves a little bit of itself behind, and gradually the bed builds up. And it basically consists of the tail ends of many, many ripples that have migrated through over time, and the final deposit is thinly laminated, but it was deposited by ripples. And that's a pretty universal theme that we have seen in many rocks, all the way from Archean to modern. Okay. So the physical process of flocculating mud and then having transportable floccules building ripples and beds and stuff like this, that has been going on, because physics didn't change, hopefully, over the last 4 billion years for a long time. And there, just normally when people think of mudstone, they think about clay and stuff like this, but I didn't mention the minerals. We do, of course, experiments with clay, lots of them, but it works. And I also mentioned, however, that it also works with however fine the stuff is. Fine stuff here, like coccolith, for example, less than 10 microns usually. This is pure coccolith sediment, basically. It flocculates. It forms quite nice large floccules, and it builds up beds. So a coccolithic limestone that's laminated, in my opinion, was probably also deposited by migrating ripples that consisted of flocculated coccolith. In the laboratory, in the flume, this is how it works. Exactly the same. Different mineral, but the rules are the same. We're planning to do experiments with all other sorts of other crazy things, like maybe feldspar dust or olivine dust or something like this. And I guarantee you it will still behave the same. So this is just, I showed the coccolith experiment. And this is literally just came out of the lab a few days ago. And we have here fresh water, 2%, 3%, 3.5% salinity. And you notice that the systemic decline curves get steeper at about 25 centimeters per second, which is the same what we see for clays and silts and stuff like this. So basically, the bed load floccules form at critical velocities of sedimentation that are common to other fine-grained materials. And I expect, and I've already shown this before, this happens regardless of mineralogy. It's just when things get small enough, they want to flocculate. And here, this is a picture actually from an outcrop in Romania, the bituminous malformation. And this is basically cross-bedded mudstone. Okay, this is a mega ripple that is the next bed form up from the ripples, basically. And we have pictures that a student of mine gave to me from ODP 401. And here you see also it's a mudstone, and you see inclined bedding here. It's sort of quite similar to the stuff that you see in outcrop in Romania. And we have other examples of these kind of cross-bedded intervals in mudstones elsewhere. So in summary, muds and clays are prone to form large floccules over a wide range of conditions. Aggregates that travel in bed load, form ripples and higher order bed forms and build up muddy strata. The pelagic settling of mud components is commonplace, but pelagic input is invariably reworked and reshaped by bottom currents. The coarse sand and silt that is interlaminated with mud layers does not automatically imply a change of flow velocity because these things can be deposited at the same time under the same shear stress regime. The erosion of seafloor muds produces soft clasts that can be transported by bottom currents and then accumulate to form new mud beds. And in many respects, looks very much the same as the ones primary deposits. Mudstone lithics, anywhere from millimeter to micron size, are a common component of marine muds in both shallow and deep settings, and they also imply bottom current activity. So this is sort of there's a short version of what we have been doing over the last 20 years, and we're still finding new things, but fundamentally, there's no reason to believe that mudstones need low energy conditions to get deposited. They actually seem to deposit just fine when energy conditions are much higher than what normally they're told they need to deposit. We have shown it so many times in flume experiment, there's no question about it. And so I don't know if I've exhausted my 15 minutes or not, but this whole topic, I could talk about for hours and show you all sorts of beautiful pictures of it that makes a point, but maybe some other time. But it's in 15 minutes is about all I can do. I primarily wanted to point out that there is a process that is natural, happens all the time, wherever you go, when there's suspended mud. And that is a process that probably deposited most of the mud that you see in the rock record. Okay, thank you.